If you've ever taken physics, you've probably heard of E equals mc squared. Now what's less known, unless you've taken calculus, is that Newton kind of sort of maybe invented calculus. I don't know, watch my short. Now if you want a derivation that uses stuff from AP calculus and AP physics, but doesn't really explain the whole energy of a photon part, take a look at this. But here's a more complicated explanation that definitely won't be boring. No!
I accidentally attached my dog into the car and took my wheel for.
Now before I start, I have to make sure that you actually understand special relativity. Imagine you're standing in the middle of a highway. Don't actually do this. And two lightning bolts flash at the same time, at the same distance away from you. You would naturally see these lightning bolts at the same time because the photons or the light particles move at the speed of light and come to your eyes at the same amount of time. Now, if you're in a super fast car moving really close to the speed of light, and at the instant you're in the center of the two strike zones, the two lightning bolts strike, logically, the one you're moving towards is seen first because the photons from the front lightning bolt will meet you first in the front, and the distance from the back lightning bolt increases as time increases. Now when you think about it, you're viewing the same event that logically occurred at the same instant, but you're viewing it at two different times because they're in different situations. This means that different speeds can change the perception of events. Now, this is because speed actually changes your perception of time, and this is why relative timing occurs, and the only way to really counteract this is to calculate time drift from a stationary point. But that's nerd stuff. Essentially, Einstein just showed that Newton's laws didn't really work at really great speeds, which is also why he didn't really disprove Newton, he just refined his laws. Also, Einstein said that mass bends space, which is also time somehow, and that bending causes gravity and attraction, but that doesn't really matter right now. You just need to know that he refined his law. Also, E equals mc squared just means that energy equals mass times the speed of light squared. This essentially shows that mass and energy are kind of the same thing, and that you can kind of create mass into energy and energy into mass, disproving the idea of conservation of matter. Let's start with ds squared, which is a space-time interval, which just means some change in space and time. This ds squared is invariant, which means it doesn't change over different perspectives, or reference frames. Now, can you prove that? I don't know. Go ask ChatGPT. Why is that the way it is? Alright, so if we have a reference frame S prime, and we take the space-time interval of that reference frame, we get c squared dt prime squared minus dx prime squared minus dy prime squared minus dz prime squared. Now if we use this thing called the Lorentz transformation, shown here across this several x prime, y prime, z prime, and t prime, we can actually plug into the original space-time interval. Now, in order to find the derivative of these in general, not respective to any single variable, you have to take the total derivative, which looks like this, involving partial derivatives of the variables in each question, but not the constants, such as c and v. Alright, so moving back to the equation we had before, we actually get this new expression. And when you distribute, you can actually cancel out the c squares in the dt expanded version. And then once you do that, you can actually cancel some terms within that dt. Now, if we actually factor out dt squared and negative dx squared, we can actually get c squared minus v squared with the dt squared, and also 1 minus v squared over c squared for the dx squared. Now, if you wondered what the lambda was from before, it's actually the Lorentz factor, which is 1 divided by the square root of 1 minus v squared over c squared, making lambda squared just 1 divided by 1 minus v squared over c squared. So, when plugging in, you can actually just get dx squared because the 1 minus v squared over c squared in that distributive is actually cancelled. Finally, if we take the 1 in the denominator and we just convert it to c squared over c squared, we get c squared minus v squared over c squared as a denominator, which means that the c squared minus v squared are cancelled, leaving c squared dt squared, and leaving the original ds squared of c squared dt squared minus dx squared minus dy squared minus dz squared, making the space-time interval invariant. Let's move on to action. Action is defined by the integral, or this fancy s, which is just area under the curve, from time 1 to time 2 of the Lagrange function, which is just the kinetic minus potential energy, which is the energy of motion minus the stored energy. Thus, action is just like the total effort taken by our particle. Now let's say we're at a reference frame S, like this, and this particle is moving at at a velocity v. And let's say we want to measure the action taken by this particle as it moves from two world points, which are just coordinate points with time, of A to B. Now, coordinate points have x, y, and z, but they also have ct, speed of light times time, because you're measuring time as a physical quantity. In this case, the action becomes the integral from roll point A to roll point B of a constant proportionality, let's say alpha, of ds, because it's going through space-time. But let's say with our particle, our reference frame is moving with the particle, so the x, y, and z positions don't change. This means that ds squared is equal to c squared dt squared. Now if we just say over time, it isn't that accurate because, as we learned before, time can change for different people. But if we pretend that the particle has a watch on and we check that watch's time, we call it proper time, and this is more accurate. This is why you actually rewrite c squared dt squared as c squared d tau squared. Now, a little fun fact about d tau. If you multiply by this unimportant thing called the Lorentz factor, you actually get dt. Except this isn't a fun fact, because that means that d tau is equal to this, and the Lorentz factor is one of the most important things in special relativity, and that I lied to you! Now if you remember from before that ds squared is equal to c squared d tau squared, we know that taking the square root of both sides, that ds is equal to c d tau. This means that the integral from a to b of ds is equal to the integral from t1 to t2 of c d tau. And we know that d tau is equal to dt times the square root of 1 minus v squared divided by c squared, leading to this a formula. But wait a minute. Look at this square root. Since we know that nothing can surpass the speed of light, this square root has to be at most 1, because the fraction can't be equal to 1. Now if you think about it logically, multiplying cdt by a number less than 1 would make it smaller, and therefore would equate it to the integral of a to b of ds. This means that we can conclude that the integral of ds is less than or equal to the integral from t1 to t2 of cdt. Now since it's a less than or equal to sign, we know that the integral of ds has a maximum value, but has no real minimum value. Now, this is an issue because in variation calculus, you typically want to minimize or find an extreme, which is technically minimize. But CDT has a maximum, and therefore we just have to make it to a minimum. And we can accomplish this by simply negating the constant of proportionality from before, alpha. And this is why we actually have a negative alpha sign. Now if you remember from before, action is just the integral of the Lagrange function over time. And from our newly derived expression, we can conclude that the Lagrange function is equal to negative alpha c times the square root of 1 minus v squared over c squared. This can also be written as negative alpha of c, 1 minus v squared over c squared, raised to the power of 1/2. And now this is where things get interesting. Now you may have learned binomial expansion in algebra class. However, you can also do binomial expansion with fraction exponents. However, the expanded version is really an infinite series, and really only works when there's a fraction and the numerator is much smaller than the denominator. In our case, v squared will always be much smaller than c squared, and when you expand it, it leads to this really big expanded form over here, but we can simplify it to just 1 minus v squared over 2c squared, because anything beyond that is it's essentially negligible, so you can just essentially just cut it out. Now, comparing it to the Lagrange function, but expanding the kinetic energy, you can see similarities between our the distributed version of negative ac 1 minus v squared over 2c squared and 1/2 mv squared. In this case, you can cancel, and you're left with this. You can see that m is just equal to alpha over c squared, and that means that alpha is equal to mc squared. Now I know this is getting a little crazy, and probably a little boring. I want to entertain you a little bit. Alright, that should be good. Now if we plug in our alpha value into our function, we get this new expression. Now this expression is really important because, plot twist, I didn't tell you about another equation. Energy is equal to a dot product of momentum and velocity minus the Lagrange function. Alright, so starting with momentum, or p, is equal to the partial derivative, which is just this fancy little d, of the Lagrange function with respect to velocity. Now, the details of this don't really matter. It's Calc 3 material, and I promised a basic explanation, but it's just the rate of change of the Lagrange function with respect to velocity. Now, calculating this, you end up getting mv times the Lorentz factor, gamma, which is just mv over the square root of 1 minus v squared over c squared. Alright, so if you were a keen observer, you might have seen that the momentum and the velocity from before had little vector symbols, little arrows above them. Now, this is because there truly are vectors, and when you're multiplying vectors, you have to do the dot product or the cross product. In our case, we're doing the dot product. Now, the dot product is more complicated than just multiplying, but for our case, we can just say it's multiplication. So it leads to this top formula of, and if we divide the mc squared, the second term, by the square root of 1 minus v squared over c squared, you end up getting this expression. And when you distribute, you end up getting this. And that means you can cancel out the mv squares divided by the square root of 1 minus v squared over c squared, leaving you with mc squared gamma. Now let's get serious. Childhood cancer is very bad. I mean, this may not be the formula that you're most used to, but this gamma is actually the secret component of the expression that really exists. Now, if you do want the E equals mc squared, you just want to make gamma 1 by getting the rest energy of the velocity, by setting it equal to 0, making gamma 1. I hope you were able to learn a little bit of physics, or calculus, or at least just find me entertaining for a little bit. Big shout out to Math 505. He's the guy that originally made the derivation. Everything is in the description. But it's time for me to go now. Thanks for watching. Consider subscribing, and goodbye.